3D was the ability to read a sequence and then write a transformation equation. 3E is the reverse. This time we do not know what the sequence is, and we do know the final equation. So they're saying take the graph of, did I write this the other way around? I may have wrote it the other way around, but that's okay. We're trying to take the graph of, this is your original graph, and you want to bring it to the final graph. Okay, so that's your x squared graph. If it helps you, maybe just cross this one off and write the original question. So the original question is 3x plus 2 squared plus 5. You can write it like that just to make it easier. And on the bottom, let's flip it around. So our final destination is this should have been y equals x squared. Why do I make a distinction between the two? So that you know which one's the final one and which one's the original one. So to tell the difference, I'm going to put a dash on these ones. So it's y dash, x dash. So that way I know this is the final function and this one is the original. So how do I know from the question? Because it says takes the graph of this to this. Because it says to, that means this is the final and this is the original. Okay? All right, so how do we do it? Same thing, using mapping notation. We're going to list exactly what we see. So we have original y, we have original x. Our goal is to find what's the new x, what's the new y equal to. Okay, because this will tell us the transformation if you can read the mapping notation. Right now, if I look at the two, actually it's too far below, but I'm just going to write. So this is the original, this is the new, right, with a dash. That's our new. If we do a comparison at the moment, you can see that this has a square, this has a square. What am I squaring in the original? I'm squaring 3x plus 2. What am I squaring in the new one? I'm squaring x dash. So there's a link between these two. I've substituted the 3x plus 2 with an x dash. These two are currently linked. So one way of thinking about it is you can actually say, well, that means x dash, which is this one, is actually equivalent to 3 times x plus 2 from the original function. So the original getting to the new, right? Whereas my y transformation, you can see there's a y here. Yes, there's a y here, but then what about that plus 5? See, that doesn't belong with what you're squaring. That's not the x transformation. This must be a y transformation. So you actually have to rearrange the original function. And this is what we do. We rearrange it and we write, well, actually, it should be y minus 5 is then equal to 3x plus 2 all squared. So I'm just changing the original. And why do I do that? Is so that I can say y dash must be linked to y minus 5. So original y minus 5. And this one, I can still say original x times 3 plus 2 is the same or being substituted with a new x. Now, if you write it this way, you can actually see now that means y dash, which is this one, I've replaced it for y minus 5. So it should be y minus 5. So far, so good? Okay, and then at this point, some students feel, especially after 3D, they start rearranging things. You don't need to, because what was the goal? The goal was to find y dash, x dash. Already got it. Y dash is y minus 5, and x dash is 3x plus 2. It's right there. It tells you what to do. Yeah? So if I actually had to read the transformation, it was 3x plus 2, y minus 5. And if you think about it logically, it makes sense. See, x squared is this original graph. This graph, well, I clearly had gone left by 2/3 and up by 5. So left 2/3, up by 5 is somewhere over here. So obviously, if I want to go back to this spot, original to final, don't I have to go, instead of going up by 5, I have to go down 5. That's what I'm saying. Down 5. That's what I'm saying. It says down 5 here. Down 5, So yes, I go backwards, I go down 5. Instead of going left by 2/3, well, yes. Well, you can actually take out the 3 as a common factor and it becomes right by 2/3, but same idea, dilation before translation, up to you. But it makes sense that I've read this transformation description sequence is explaining what's happening. It's obviously got thinner and it's got a movement, but we can see that I'm going backwards. I'm going down and then I'm going back to the right, and that is right by 2. It's just that there's a dilation. That's why it's right by 2. Okay, or if it helps you to understand what I'm saying, take out 3 as a common factor, and that means exactly the same thing. Goes to the right by 2/3, and it has the dilation factor of 3. That one was dilation factor of 1/3. To go backwards, we would now go dilation factor 3. Okay? So yeah, don't confuse at this step. This is why I think it's important to put the dashes when you're first starting with mapping notation. It helps to see which one's the final, which one's the original. And your goal is once you map them together, sometimes you do have to rearrange them. This case, you didn't have to. This one was nice. There was no rearrangement that you had to do. Okay? Can someone actually check in their exercise 3E question 3b? Did I write the question wrong? Was it x squared moving to 3x plus 2 squared plus 5? It was this way. Oh, okay, cool. Well, yeah, so this is what they wanted you to do then. Cool. Usually I start off with the other way. So that way students feel a bit more comfortable moving from x squared, so a base function, to a transformation function. This one technically is transformation back to base, but I don't like thinking of it as base. I just think of moving original to final. Yep.
The textbook does it in a different way. So like they get, what with the square boxes is made.
Oh yeah.
They want to solve for old x, and then they just run a series of transformations for that.
Then that means, did they write this to this then?
Oh, yeah,
Okay, so if it's going from this to this, then it makes sense, because this right now is describing moving from this to this. If you're moving from base to that, then it makes sense to go up 5, left by 2/3. Yeah, so that's why I wasn't sure, did I copy the right question or not? But anyways, that's an example of 3E. So you can see the difference between 3D. 3D was you were given a sequence, you get to the equation. Now it's the equation going backwards. I'm going to do one more example, okay, so you can get a feel of it. Let's flip over to the next page. Here we go. So this is now 3E, and this is a mixture of functions. Okay, it doesn't always have to go from base to a transformation. It could be a transformation to a transformation, right? So again, if I copied it correctly, then it's asking now the sequence transformation that takes the graph of this to this. So this means this is the original, and this is the final. So put a dash on it if it helps you to see the difference between the two. So here's my original, and I'm going to my new. So I want to go to y dash is equal to negative root of x dash plus 6. Okay. Same idea. Our goal is to find what is the x transformation for the new one and what is the new transformation to get to the new y, right? So here again, same thing. If I would, I don't like looking at the x transformation first because it's the most obvious. So from here, we can see that I've got a square root function. I've got a square root function. So what am I rooting here? I'm square rooting 4 minus x. What am I square rooting here? I'm square rooting root x. Oh, sorry, x dash. So therefore, these two are matched. Therefore, this is what I'm replacing. I'm replacing this entire thing with an x dash in the square root symbol. So therefore, you can say, well, x dash, I'm replacing it with 4 minus x. But then what's the leftover? The leftover here is I still have this plus 3, this 2, and that's why that must be the y transformation. Same thing with this one. I've got this y transformation on either side. So what I do is I usually just bring it all across. I just bring it all onto the one side so that I can see all the blues on the blues and all the yellows with the yellows. So if I do that, I'm going to move this across. So that's now y dash minus 6 equals negative. Oh, sorry, I just realized there's a minus there too. So let's do that. Okay, so I just moved the 6 across and divide both sides by negative, and I just kept the brackets on the outside. Okay. And then same thing with this one. I'm going to move the 3 across and then obviously divide everything by 2. So it'll be y minus 3 and divide them all by 2. So halving it. Okay. Hopefully, hands up if I'm going slow enough. Does that make sense what I'm doing? I just rearranged this one to keep all the y's on one side. And I just kept root of x. Same thing with this one. I rearranged the new equation, so the final equation, so that all the y's on one side and it's just a root of function. Why do I do that? Because now you can see x dash matches with 4 minus x, which I already wrote over here. Then I can say this transformation, whatever this is, I'm replacing this. That's what I'm pretty much rewriting. I'm just swapping them. So that now equals that. That's how I'm getting to the new one. So if I do that, you get now negative bracket y dash minus 6 is equal to half y minus 3. There we go. And now from here, this one's already sorted. You know what x dash is. You're done with that one. There's nothing you need to do. But this one, you need to rearrange. This one, our goal is to find y dash. So move everything across. Just make y dash the subject. So here, times both sides by negative, and I get y dash minus 6 is equal to negative half y minus 3. Cool. So far, so good. And then to get rid of that minus 6, add 6 on both sides, and this is what you get. Y transformation is equal to negative half of y minus 3 plus 6. Now, this is what I was trying to explain to you last session. In the exam, there's many ways on how this could be the correct answer. Often, Dr. T, which is really just BUDMAS, because BUDMAS means brackets, indices, division, multiplication comes next, and then addition, subtraction, right? That's what this is. Dilation is multiplication, division. Reflection is still multiplication with a negative. And then T is add, subtract. It's in the order of BUDMAS. So here, you can leave it like this. So sometimes they write their sequence exactly what you see here. So notice I didn't move anything besides just, once I divided, I didn't expand that. I just left it exactly what it was. I just followed the order of inverse operations, and then now I'm just moving it back in inverse operations. So sometimes you'll see the answer in sequence exactly this. So if you read this sequence, this means original y, you're going down by 3 first. Then there's a dilation factor and a reflection. And then right afterwards, there's a translation again. Yeah? So this is what I'm saying. You can follow exactly BUDMAS by reading what you see, and it could be one of the answers if it's a multiple choice question. Otherwise, usually, just for my own sake, I like Dr. T, if I keep it cleanly, I just expand everything. So if I expand everything and keep it clean, this is where negative half times y, you get negative half y. Negative half times the negative 3 becomes positive 3 on 2. Plus 6 means I can combine those two together. And my y transformation looks like this. Now, what's that? 12 plus 3, 15 on 2. So that's what, 7.5? Yeah. So that is Dr. T. That's your dilation reflection. And that's your translation for the y component. So that's what I mean, like, I like it clean this way, but this is not wrong. So if it's a short answer question, this is fine. Your examiners usually should tell you which one they prefer. They might write a template like this. They might write a template like this, but they should generally guide you if it's a short answer. If it's multiple choice, there's a whole variety of possibilities that might occur in between. And all of them will give you the same answer. Okay, so no matter how you do it, the answer will still be correct. So you can move down by 3, dilate, reflect, and then move up by 6. You'll still get the same answer had I just dilate, reflect, and then went up by 7.5. Would have been the same answer. Okay, because it's a net result. This is like 1.5, add 1.5, and that's plus 6. So 1.5 plus 6 is still the same thing. You know what I mean? Question?
If you station it in like a different way, like you get the same graph, you station it both ways, but like if you station it the first way, would you like get marked down if the answer was the second way, or is it?
They shouldn't penalize you, or they can't really penalize you because it is the correct answer. It just means their question needed to be more specific. And knowing VCAR, well, actually, I don't know VCAR now. Our last 2 years, they've had mistakes and errors. But assuming that they were, pretty clear and did lots of double checks, usually their questions are very direct. They'll tell you exactly how they want it. I just like it for myself that it's clean. So I stick to Dr. T. I mean, I know it just looks clean. It looks clear to them as well. Whereas this one, maybe I may be likely to make mistakes. So I just prefer this one for myself, unless they had a template. So they might have told me to feel out. They might have had, they could actually do something like this. They might actually do dilation of factor half, then they followed by reflection, and then they say, fill in the translation, fill in the missing blank. Then obviously following this order doesn't make sense. It doesn't match that sequence. Then it forces you to go to this one. Or it could have been the other way. They might have done a sequence where they say it's translation first. So they might say, translation of down by 3, and then they say dilate, and then they say reflection in which axes, followed by translation of what? Fill in the missing blanks. Then there has to be this one. Yeah, so they usually have to give you some direction and template if they want a specific answer. Yeah. And short and multiple choice, they could have chosen any of these, and then you have to explore. So you might got this answer, but they may have used this answer. Yeah. And therefore you have to extrapolate and go backwards. That's why mapping notation allows you to figure it out. Whereas if students just learn to read it directly, it's cool, it's good. But things like that, where there are the nuances to it, that's where if you don't learn the skill, you kind of cap yourself out of that possibility. Yeah. So just learning how to do mapping notation, that's one of the key steps. All right, so now that I've got Y dash for you, so here we go. This is assuming that this is the final and that's what they want, and they want Dr. T, then my answer to the top would be it's negative x. Remember BODMAS, so negative times the x first. Then I add 4. And then this one is negative half y, add 15 on 2. So if you were to read or describe the sequence now, Dr. T, so I can see dilation is dilation of factor half from which axis again? From x, because it's affecting your y, so vertical stretch. So half, actually I should write it down in case you guys aren't following too quickly. So dilate factor half from x-axis. Then the next one is reflection. So I'd say reflect in x and y axes. Okay, so I've ticked off the negatives, and now it's just translation. So translate, you can say 4 to the right. And was it 7.5 up? Yeah, 7.5 up. And there's your Dr. T sequence. Okay. That's 3E. 3F does the same thing, but you now have to sketch it. So I might give you the actual function and say, sketch that. Sketch the original, sketch the final. And that's what they do. Yeah, so that's 3F, 3G, 3H pretty much follows that. 3I's transformation notation. Cool, so copy those notes just so that you get a feel. So when you have a transformation to a transformation, this is the one step you do. Okay, it's one of the ones I notice students who don't practice enough, they will struggle here. Okay, it doesn't always have to go back to the original. So most of the questions you do in your textbooks always starts off with original to a transformation, and then transformation back to the original. It doesn't have to be. It literally could be any function you can come up with. Yeah, so it could be a transformation to another transformation, and that's often the ones they do in the exams. They wouldn't do this one, where convert this to that. That's what you did in year 11. Okay, so in year 11 was just understanding how the mapping notation works. Nowadays, it could be, they'll probably swap that around. It's like negative a third, 3 minus x plus 2/3, I don't know, something like that. And map that to negative 5 root x plus 2. I don't know. So that could be an example. Move from this one to this one. How would you do it? Something like that. Okay, so that's the idea. All right, team, that finishes 3E. I'm going to stop the video there. Then we're now going to get ready to get onto 3F. So the essence to take out, remember the core exercise is 3D, 3E. 3D and 3E, moving backwards and forwards.